going to talk about Servant, a fairly recent library which was initially released in last December, I think. And I'm going to motivate it first by explaining what was wrong with all the libraries we already had, and how we basically solved this problem and discovered pretty much a new way to write the web application we're used to. So I'm going to ask you, what do you think could be wrong with this code? If anyone has got an answer to offer. So this uses the Scotty library, which is quite minimal and looks a lot like many web frameworks in other languages. So you had sorry? So that part, like, it's not too bad. I mean, when you have you might give like a list of roots in a data type and things like that, like it is done, I think, in Yesod, for example, right? So this might be considered wrong, but that's not the part I'm concerned about today. So one thing, yeah, it's that we are extracting the parameter inside the request handler, whereas it should really get it from the web framework and only focus on what it has to do within the handler, and not worry about decoding or read parameters from somewhere in the request. And more generally, the answer is that, as you can see here, all this information, so the path at which the endpoint is reachable, and all the parameters we are using, so query string parameter and the request body, all of that is not accessible from the outside. So if you're looking at the code, sure, you understand it. But if tomorrow you have to write a web page that talks to this service, or a command line application that sends a request to this service as well, you have to start from scratch. You don't have any information to use that will save you the boilerplate of going and looking at all the endpoint declarations and taking a look at all the parameters that are used and so on and so forth. So basically, the problem we identified was that we were writing web services, but when we wanted to talk to them, well, it was all wasted. All this information, we couldn't reuse it in any way. And by the way, the problem is the same in other languages. So this is a JavaScript, a Node application I've asked someone to, which should be equivalent to the previous one. I've asked someone to write, and it exposes the same problem. Even in JavaScript, you don't get to inspect the structure of the application, the endpoints, and the parameters. So you really start from scratch whenever you want to talk to this service as well. So like I said, whenever we want to talk to them, we start from scratch, and this was not good for our purposes. And there are many sources of information in a request, and all of them, well, we know where we can get data from, yet when we write a service, we don't get to say, hey, remember, I'm taking this parameter from there, make this information available to anyone who wants to talk to my web service. Plus, if you do it manually, of course, you're going to sometimes make a typo, you're going to forget a parameter, or you're going to use the wrong, or you forget a field in your JSON, or things like that. And if it was just for this, it will be fine, but we have the information. I showed it in the previous slide. It's right there. Why can't we exploit it? Well, we can. So the plan will be, instead of writing directly the web service like this, we could describe it. We describe the endpoints just enough to synthesize the information we need to generate, for example, the client functions that can query the web service in a correct by construction way, or by generation. So you make sure you generate the client functions fine for the query string parameters, for the request bodies. And the idea is that it's enough. If you know all these things, which parameters under which path does it take a request body, if it does, what's the type, and so on and so forth, then you're done. You have all the information you need, and you can actually generate the client functions. And you are saving yourself a lot of time and a lot of debugging, because when you do it manually, you always spend 10 minutes here fixing this little problem because you forgot to add some parameter or something. So we want to describe it. If we describe it, we can then make sure the implementation matches the description. If we are smart enough in the way that we, if we go far enough in the checking, basically. And then once we are sure that the implementation corresponds to the description, we're all good to go to reuse all this information and generate client functions. We can think about API docs that are generated semi-automatically. We can do many things that you will see later in the talk. But now, how do we design such a description language? Well, it would be nice to have it, of course, be in Haskell, because the web service is going to be written in Haskell in my case. So might as well just have a direct connection and have some types that go between them, and that make sure that we are not doing something wrong on the way. However, we wanted the description language to be open, which means we want to be able to add new constructs. Of course, we're going to have things to describe query string parameters, request bodies, and HTTP methods. But let's say tomorrow I want to add my precise vision of authentication, how it should work in a web application. Then if I can't express it with the base constructs of the language that we designed to describe the applications, then there's no way for me to just plug in some custom description for the authentication. So we want to be able to add new constructs. So listing just all the possible constructions, like HTTP methods, various parameters, in an ADT, that wouldn't work, because when we need to add a new case, then we are breaking everything, all the code that relies on this ADT. And it would be nice to have a description that forces the implementation, the type of the handlers change whenever you change the description. If you describe only one endpoint, it shouldn't work when you supply an implementation of a server for 2 endpoints, right? That seems logical. And then if you're returning a user instead of returning products, which was expected, it's the same. You would like it not to compile. It shouldn't be you shouldn't be able to run this, because it doesn't make sense. So I don't know if you remember Leonard's talk from yesterday. But so we are saying that we want a description, so some value or something. And when it changes, it impacts the types of other things. And in Haskell, as you know, you can't make that happen if your description is a value. You can't have a value that changes the types of something depending on what it is. So the solution is to describe it with types. Because if you change a type, then you can change something when, basically, if you have int, maybe int is some other type. But if you take char, maybe char is different from maybe int. You can't tell GHC that those are the same. It won't agree. So the idea is to do the same, but instead of having int and char, we will have some descriptions of APIs at the type level. So I know this might be a hard sell, but we've done our best to make it as nice as possible. That will be a way to say it. And I think it actually works out pretty nice in practice. Once you're used to it, it's okay. But I reckon this might not be the strongest selling point of Servant, as you will see in a minute. So let's take our previous example, let's go T1. So a post endpoint, a query string parameter, a request body, and then depending on the parameter, you reply with the request body in lowercase or uppercase. So how does it look? This is the description. You'll notice that we are using, like in Nanotalk, some extensions. I haven't listed them all, but there will be 3 of them, I think. So one of them, as you can see, fits quite nicely. So the type level strings are used simply for the static path fragments, where we are just saying this will be an API with an endpoint that listens as /endpoint. And then we have various flavors of parameters. Query flag is just a query string parameter considered as a Boolean, so you don't have to specify a value. Just putting it there makes it true, and its absence makes it false. So then the request body, and an interesting thing happens here. Look, there's plain text in this list type of thing. So if you remember from Linus' talk again, JC now supports lists, but at the type level. So what we're using it for, I won't bother you too much with any implementation details, how we use it, how it's implemented and whatnot. But we specify all the content types from which we want to be able to decode our request body. And the same goes for the post method at the end. So this says this is a post endpoint, and the response will be in plain text format, well, with the plain text content type. And the thing represented there will be just a piece of text. So nothing too complicated so far. Are you with me? And now the implementation. So we kept the function that we had earlier. And then the endpoints. It's quite straightforward. So now there's this interesting thing here. So it means that depending on the API that we wrote above, this computes the right type for the request handler that implements this. And I've put in a comment that shows the actual thing this ends up being. So don't worry too much about either T if you're not familiar with it. The idea is that we list the parameters here, and then the handler just gets them as arguments automatically for you. And that's because we believe we should not have to worry about decoding, and especially handling decoding failures and things like that. This gets in the way of clearly seeing the logic of what happens in your web service or web application. So we just went with something that decodes the parameters using the formats you specify in those lists, and you get them as arguments automatically. And since this is a monad, you can use return. So the servant error bit just means that you can do what is promised up there. This means returning a text, but you might as well return an error in case an HTTP error, in case something goes wrong and you want to signal it using the typical HTTP conventions. So 400 error code or something. And then the main, which this function is from servant serve. We pass it the request handler here, but then we have this little API, and we see it's simply a proxy. So you've probably heard about proxy yesterday as well, but I give it a little slide here if you want to have another way of looking at it. So it let us simply target a type, but using a value. This gives us the possibility of asking GHC that he checks the implementation, the endpoint function from before, against the description that is described by this proxy, which means the A on the slide there will be the API type that we saw previously. So it lets us say, okay, here's the description, and we have an implementation here. Can you please check that it matches, it has the right types and the right shape and everything. So I said we couldn't reuse information with the previous solutions. So now we have a description, a simple one, but still. What can we do with it? Oh, yeah. Yeah. This one. So there's two things. The first is that you don't necessarily need to trust the implementation, because when you have server API, you can't deduce, well, JHC can't deduce what API is. It only knows what API gets mapped to, which is this type. So and type families, this is a type family, because it computes the right thing and it uses the type family extension. They are, for now, not injective, which means if you have a server of some API equal to a server of some other API, you can deduce that the API were the same to begin with. Actually, we have perfectly reasonable examples of two different API descriptions that get mapped to the same handler type. For example, if you just switch post to get, this is the case. Because post, get, all these things are not what your handlers should worry about. Your handlers should just take the parameters and produce some value that you're going to send back in your response. Well, that's our take on it anyway. So if you change post to get, this doesn't change. The type is the same. And yet your API type is different. And the second thing is that you actually want a central description where you put everything as you expect it to be. And then you have something that checks that you're not doing something wrong in the implementation. If you didn't have this proxy argument, you will just have the implementation, and this will be your central description, which is not exactly what we're going for. We want something that's separated from the implementation and stands as a reference about your web service or web application. Yeah, if you have any question, just stop me and ask. So yeah, what do we get when we describe things like this? Well, functions to query the API come for free. This little this client function here comes from servant as well. You can see it. We call it in a similar way to the serve function a few slides ago. So it's again, it takes the proxy, because that's our main. This is our main point of information. That's what we use the most in servant. Except that it only takes that, because this is the host where we want to send our HTTP request to. So that's not related to the API. So the only thing it really asks for is a description of your API, and you get client functions for free. Now some usage. If you don't ask to get an uppercase response, you get a lowercase one, and if you do ask to get an uppercase response, you get what you expect. And I said we had these lists where we can list the format from which we want to be able to decode or encode things from or to. Well, there are lists, so we can put several things in a list. And this is a perfectly fine example of offering several formats for interacting with the outside world. Say you want to, you have to rather interact with old Java APIs using some weird XML files and whatnot. You could have an XML content type there, and as long as you provide a way to decode, well, serialize or deserialize from your XML, you can make it work with servant. And there's nothing special about plain text or JSON. You can just define your own content types and make them work in the very same way. And this is taking it to the extreme. It was, I think, Julian right here who wrote, or someone from Australia, or you worked on it together, I don't remember. So Timo van Alt, yeah, in Australia did this. So he wrote a little library to provide content types for images. So as you can see, instead of JSON and plain text, we get image types, content types. And then the handler is simply returned, because we are not changing the image. Once it's decoded into this thing, we don't change it, we just return it as is. This is the same image, you can take it back. Except that depending on the content type and accept headers, you're going to get a different format back. So this basically is an image conversion web service or web application, if you make an UI for it, whose handler literally does nothing. And we think it's a good example of why it might be a good idea to separate all this decoding business from the actual logic. Because here we realize that decoding is actually the meat of the work it should do. And we indeed realize that the handler does nothing interesting. All happens in the decoding and encoding bits when you get the image and then send it back. So we can as well get JavaScript functions in the very same way, really. You'll see instead of client, we are using this function. It again takes the proxy as usual now, and this returns a string. So this isn't great, of course, but this was the first approximation, and nobody stepped up to write this with something that nicely generates JavaScript in a safe way using a nice library for it, a nice pretty printer. But we generate valid JavaScript. We have tests for this. And it works in the very same way. And for example, you could do what I do on this slide. So you generate a JavaScript file from there. You write it to wherever appropriate right before you launch your web server. And this basically guarantees that your JavaScript interface to your web service never goes out of date. So if you have any questions so far. Yeah. So this is a topic we've been discussing for a while now. So have you heard of A2S? This is a way to instrument a web API with metadata that points to all the existing endpoints. So for example, if you have, say, /users, and then you have a bunch of endpoints under this, like to get some particular properties of users, the idea is that in those places where you don't have any existing endpoints, it will insert some and say, hey, if you want to get the list of users, go to this place. If you want to get a particular user, this will be right here, etc., etc. And with another separate solution to this will be to have something more like we will serialize these API types and send them over the network, and then somehow read them back as a type. So this is not something we can do in Haskell right now, as far as I know, but this will be something you could do in a dependent type much more easily, I think. Yeah, basically that's the idea. Yeah. 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 You remove this and you make it another declaration. Yeah. Oh yeah. It's basically as long as it's basically the checking happens at this point, And it compares the API you're talking about. It knows exactly which one it is because you have a proxy that says this one. And then you have a bunch of request handlers. They might be wrong, we don't know yet. And then using this, we compute what we were expecting to see in your request handlers. If you 1, 2, 3, or dozen, and the types they have, if they have the right types, the one we expect. And if all those checks pass, then you're good to go. It will be valid. And this is all we require from you. Basically, is to have something at this point when you call serve that has the right shape for this proxy, well, for this API. So serve directory here, and so it doesn't work. It won't compile.
Right.
So that's what I meant when I say that we want a description that affects the server, the implementation. So the type, in the types, we want it to be reflected in the types. Yeah. Yep. Yeah. So yeah, I didn't say much, but we use row for as an escape hatch, basically, where we, if you want to integrate, say, a YesSod application, you could. You just declare a row endpoint, and then you put it. That's just the application. For those who know why, we just expect something of type application here. So we are serving static files this way, and you can do many other things. Someone even wrote a WebSockets integration for Y that plays well with servants. So you can have a row endpoint, and instead of file serving here, you will have your WebSocket application running under some path in your servant thing. So we can also define mock servers. And by mock server, I mean a server that will have the right endpoints and everything, except it will just respond with garbage, like data with the right shape but random values, filled with random values. And as usual, we just call a function on our proxy. So you see this is the same as file serving as before. But this time, we are replacing the endpoint implementation, the right one that calls the right function and everything. We just replace it with mock API. And we are able to, as long as you have a random generation instance for the response and request body types and whatnot, this will just work. This is an example of response, fascinating. So to sum up, every time you see we take a proxy. That's the first thing, because that's the central description of our application or API. And this is what servant cares the most about. And most of the library revolves around it. So the server implementation checks against the server implementation is checked against the API. If it goes fine, you get an application. Same for the client. Mocking works the same. JavaScript we saw as well works on the same model, and everything we do basically will forever have this shape, because this is the way, the handiest way we could do things with GHC Haskell these days. So some might criticize this from a dependently typed point of view. But from now until dependent types have libraries for running fast web servers and things like that, I think we're better off being happy about these fancy type level things and trying to make them work as nicely as possible, even for beginners. But it all revolves around the type level description, and then you do whatever it is, you interpret it in a way for the task at hand. So now you saw I used request body, posts, and the content types. So they are almost all empty data types. So this means that there's no equal and nothing at the right. So you can't build a value of those types. It doesn't exist. They're only there as a symbolic token, so to speak, in order to give that description. And the description really is just symbolic. It's just what it is. There's no value of this. And we can't do anything with it except browse the types that are in it and do something depending on what you find. And now having types is interesting as well, because types are quite a first-class citizen in Haskell. So if you see that you're writing the same main points all over again, but just with different types, you can just remove the user that you had here, and the user ID that you had here, and you just make them type parameters. And then you can even abstract away the static path that you put on front and make it a symbol like you saw in Linux talk, so type level string. And then you just basically use what you just defined and say, okay, I want a resource that's under /users, and using this to index my user type. And same with products. And the only thing left to do now is to facilitate the implementation. So you can offer a little function like this that will take the arguments to actually implement the request handlers, and it will just stick everything together for you in the right shape so that you get the expected shape for a server of resource with those types. And given that I and A are used right in those functions, you don't even have to type annotate a call to resource, and this will actually work as it is written, provided that you have these functions lying around. So you could even go further and wonder, hey, maybe I could derive the whole thing and have this implemented for me, all those functions. But then it becomes quite involved. I think you'll have to be really brave to generate SQL from the data type declaration in Haskell and things like that. But I don't see any reason why it would not be possible, at least. I said we could extend the language. Or maybe if you have any question before I go into the extension bit. No? All right. So if we want to extend the language that we use to describe the endpoints, so we saw that there are empty types. So let's just define an empty type and say we want to log any IP address that hits our web server. So an empty type, simple enough. And now this will be the only Has server instance that you will see in this talk, because while this part is kind of interesting, those tend to be boring. And you basically take the data you want out of the request. You check that it matches whatever you're expecting it to, and you call out then to the rest. Basically, the idea is that if you see log IP in an API type, and then something with this little funny operator, so the type of the handler isn't affected. So a little comment, you see that it's not server, but server T. And it takes an additional little parameter there. So it's not a big deal. I won't talk about it in this presentation, but you can have another type for your handlers, not either T, servant, error, or whatever. You can have whatever monad you like to use. And you can accomplish this by writing server T, your API, and your monad, instead of just the server API you saw there. So you will use server T and then your monad type, and it will work provided that at some point you provide a way to come back from your monad to the standard servant one. So we have some functions and helpers for this, but I won't talk much about it. So the idea here is if you see log IP, it doesn't affect the handler types because, well, it's just a server-side concern. The handlers don't have to know about it. They won't receive an additional argument or something. And so this is not worth investigating too much, but basically this is a Y application from the equal sign and onwards. So it's in I/O. This one is in I/O. So we just print the host of the client that made the request, and then we just keep routing the request to whatever comes after log IP. Yeah. Sorry? So basically, if you see this, you first want to make sure that this makes sense, the API bit. So you have to say, okay, if you see log IP in front of something I know how to handle, then I can handle log IP and this little thing. And the only way, well, the handiest way to do that is just say, let's assume the rest of the API type as an instance for our server. So we know how to interpret it, server side. In that case, then we know how to handle the API with log IP. So stick that to the front. Does that answer your question? Any other question? Yeah. So could you mix the two? Yeah. Yeah, I think basically it amounts to like having the API type of the service you're really interested in that you're proxying. So you derive the client functions in the way we saw before, and then you just use them, but from within your handler, basically. And I think you could get, except that. So either you have to proxy every single little endpoint, and then you have to. It will be a crazy amount of boilerplate, actually. Yeah. So either you proxy in an unsafe way without caring about the API types, or you have to derive a bunch of client functions and use them in the right way. I think a usual proxy will be better because you don't gain much, I'll say, by implementing the proxy with servants. Implementing the server that you're actually interested in, I think, is a decent idea, but so that you can use the client functions to proxy it. But then you're not forced to use servants in the proxying per se, I think. Any other question? So yeah, I mentioned this is in I/O, so we just print, and since we know how to handle the rest of the API, we just basically do type class recursion. In that we call it to the instance that we put above, the Has server API instance. We just call out to it by proxying this time just the API without the log IP in front, and we pass it all the data in it. So this is how to use our little thing, just the same API type as before, except with a log IP in front. And since we said that the handler types are unaffected, like we don't add an argument or something, well, we don't have to change the handlers, and this will just work. So we made 2 requests, the same we saw earlier, and we get the IP address printed to the console. So this is the first example of extending servant. And to consider other ones, I suggest we just take a look at a more serious task, because the little endpoints will be short of interesting things to do. So the idea is that we're going to build kind of SoundCloud-ish thing, but very, very, very minimal. The code for it is available in the repository for the talk. I give a link at the end. And I'll only show the interesting bits in terms of servants. So we'll need authentication because our users will need to log in, of course. Oh, yeah. Yeah, no, it's all right. So we will have a users database and basic authentication that will suffice. And we'll write new combinators for this. So the first type here is the one we'll use in our API types. We'll just say, just like log IP, except we'll stick auth in front. And this will force whatever endpoints are below to be, well, it will force users to authenticate themselves before they can access whatever is presented in those endpoints. And this is the server level interpretation of an auth combinator. You'll have to provide something with this this type, and you can write a little function that has some sane default to for these two fields. So basically, what we arrive at. So this is the instance. I skipped the boring details, but this time we want to affect the handlers type. So wherever we see auth and some API type, we want to expect something of this type with all the handlers taking a user parameter, because if it goes through, we can assume there's an user, some user data to use and have access to for example, to display the list of songs that have been uploaded by this person. Another example is file upload. I'll just skim quickly over this one. So you have files combinator. This is the one we are going to use in API types, with two backends, in-memory and temporary files, and then some helper things to make it work. This will be the shape of the instance. But more interestingly, this is how we use it. So this is the API type for the little music platform I mentioned. You can notice that we are using HTML template files. This is another library we've worked on. And this makes handlers only care about the values they are returning in these various endpoints. And then you have some encoding phase that calls out to the template and renders everything. And finally, we can see the auth and file upload combinators used. So here we have an upload endpoint. It takes a list of uploaded files and uploads them. This is a post endpoint. And it returns a user for the presentation of the upload result page. And auth is just like we saw earlier. It will auth protect this whole bunch of endpoints without the handlers even noticing. And the implementation will be like this. But I'm done. So this is the final result. If you go to the repository, you can run it and have a similar fantastic screenshot. And I haven't covered many other things we have worked on or are working on. If any of those are of interest, I encourage that you get in touch with one of us and start chatting about it. So a summary of what we can do, and the links I mentioned to the repository, tutorial, the paper, and everything. Well, thank you very much.